This video want to show that if these n vectors are non-zero and they're linearly independent, the non-zero vectors in a vector space V, well then they're linearly independent if and only if some Vj is a linear combination of their preceding vectors. Okay, so let's prove this. Suppose our V sub j is a linear combination of V1, V2 up to Vj minus 1. That is, V sub j is equal to C1 V1 plus C2 V2 all the way down to C sub j minus 1, V sub j minus 1. Okay. Then C1 V1 plus C2 V2 all the way down to Cj minus 1 times Vj minus 1. Well, that's Vj plus negative 1 Vj. So that's 0. And then I'll use the 0 vector for the I'll use the 0 scalars for the remaining linear combination. 0 V sub j plus 1 plus 0 times V sub j plus 2 all the way down to 0 times V sub n, excuse me. The last vector, V sub n, plus 0 times V sub n. Well, this equals 0. Again, this here is V sub j plus negative V sub j plus this is 0. Well, this plus that is 0, plus 0 is 0. Okay. Since one of the coefficients, namely the one for V sub j, is not 0, but the whole sum is, then the set V1, V2, up to V sub n, linearly dependent, all the way up to V sub n, is a linearly dependent set. And that's what I wanted to show. I showed that this here implies this. Now I need to show it the other way. So I went in this direction. It's the easier one. Now I want to show the proof in the other direction. I want to assume that. Suppose the non-zero vectors V1 through Vn of the vector space V are linearly dependent. Now I want to show that there's a least Cj that's non-zero, which means there's a least V sub j that has a non-zero coefficient that gives us 0. Okay, so since, wish I gave that a name, since V1, V2 up to V sub n, let's call it a set, is a linearly dependent set, we know by definition of linearly independent, we know that C1 J1 plus C2 J sub 2 all the way down to Cn J sub n equals 0, where not all the let me not say Cj's, where not all the Ci's are 0. Let Cj be the last vector whose scalar is non-zero. So in other words, in here we have plus Cj let's call it C sub k. So we know that inside here, we'll have a ck minus 1, vk minus 1, plus we'll have a ck vk plus our ck plus 1, vk plus 1, and so on. All I'm saying is this C sub k is the last coefficient that's not 0. That is, all of these coefficients are 0. So why don't we write that up formally? Okay. That is C1 V1 plus C2 V sub 2 all the way up to CK V sub k plus C sub k plus 1 V sub k plus 1 all the way down to Cn Vn is 0. However, all of those coefficients after C sub k, or after V sub k if you prefer, are all 0. So this must equal 0, because you have to have 0. This is zeros. This is all zeros. Well, what do you add to all zeros to get 0? 0. So C1 V1 plus C2 V2 all the way up to CK VK equals 0, where C sub k is not 0. Well, Okay. That implies that, I just want to see one thing. We already said that these vectors are linearly independent. So what do I want to show? I want to show that one of the vectors is the linear combination of what's before them. But that's pretty easy, because I can solve for this. C sub k, v sub k, bring everything to the other side. Bring that over, minus c1, v1. Bring that over, minus c2, v2. Right quicker than I think. All the way up to, we minus the term before. Minus c sub k minus 1, v sub k minus 1. Therefore, v sub k is this. C minus c1, v1 minus c2, v2 minus all the way up to ck minus 1, vk minus 1. All over the non-zero coefficient ck. But just to be formal about it, this is just negative c1 over ck. That's a coefficient times v1 minus c2 over ck, which is our scalar, times v2, all the way down to minus c sub k minus 1 over c sub k times the vector vk minus 1. Okay, so yeah, v sub k is a linear combination of the vectors before it. So I was able to prove that. Now, I think for completeness, let us talk about one last thing. We said that c sub k was the last vector whose coefficient was not 0. Okay, well, what if k equaled 1? Now remember, we did have c1 v1 plus c2 v2 all the way up to our cn vn is equal to 0. Now, if this is the last one that's not 0, that means that all the others are 0. So it must be that c1 v1 is 0. And that's not 0. Okay? It's the last coefficient that wasn't 0. But that would imply that v1 is the 0 vector. But that's a contradiction, because at the beginning we said that the non-zero vectors v1 through vn. None of these are the 0 vector. So it can't be that k is 1. It turns out that that can't even be. That completes this proof. If you like videos like this, please subscribe to my channel. All I do is write up mathematical proofs. If you need them for classroom homework, this is the place to come to. At some point, I will have your proof on my channel. And if by chance I don't, give me a heads up and I'll make one. Watch and learn. See you guys in the next video.